This video shows the CircuitVerse simulation of the fetch operation in Scott's CPU. We see how the instructions saved in RAM are fetched in the instruction register, and how the instruction address register is updated to point to the next instruction. This is the simulation of the theoretical video instruction code included in the How Computers Work Building Scott's CPU YouTube playlist. The link to the playlist and to the circuit are in the description.
So here we see the circuit for our simulation. Here you see the stepper. We use the first three steps to fetch the instruction. And here you see the clock generator, which also generates the clock enable and clock set. In particular, the clock enable is connected with an input of these AND gates to create the enable pulse to drive all the registers in this circuit below. The other input of the AND gates, of this enable AND gates, is connected to the right step. In this way, we are sure to create the enable pulse in the right step, so at the right moment. Similar to the set AND gates, one of the input of this set AND gates is connected to the clock set, and the other input is connected to the right step. So in this way, the output of this AND gates creates the set pulse in the right moment, and the output is connected with the set input of all the register we have in this circuit. So below the stepper we see our circuit. Here you see the ALU, of course connected with the accumulator, and the ALU has an input directly connected to the bus. This in red is the bus, 8-bit bus, and the other input connected with the bus 1, which is an element driven by a control bit, which put a 1 to the input B of the ALU, or can let pass the byte coming from the temporary register. In our simulation we use now bus 1 in order to put a 1 in the input B. Here the temporary register, we don't use it in our simulation. You see I didn't connect the S and E inputs. And above we see the RAM. The RAM is of course connected with the bus. Is connected to the bus, the MAR, so the address register, the memory address registers of the RAM is connected to the bus. This register are just a set pulse because he has to acquire the address of the cell from the bus, but it has not an enable pulse because it is not connected to a bus, so we don't need an enable pulse. We can leave the enable always on. Moreover, this RAM has of course a data input and data output, and the set and the enable with which we drive all the cell. So for example, with the set pulse we can write inside the cell, and with an enable pulse we can read from the cell. Here we see the instruction register, which contains a byte that is going to tell the control section what to do. The patterns that are put into this register have a meaning. It's like another code, and this code is called instruction code. Even this register has a set input, but it has not an enable input, because again it is not the output is not connected with the bus, but is connected with other logic gate inside the control section, so it doesn't need an enable input. Of course, it is connected to the bus because we want to fetch inside this instruction register the instruction to be decoded. And we have also IAR, so instruction address register, which contains the address of the next instruction. So what we want to do is basically take the instruction inside the RAM and fetch it inside the instruction register where the instruction will be decoded and then executed. In parallel, we want to update the instruction address register, and it will point always the next instruction to be executed. So we do this, as we said, using the first 3 steps. Then the rest of the steps execute the instruction. Exactly what will be done in steps 4, 5, and 6 is determined by the contents of the instruction that was fetched. Then the stepper starts over, fetches the next instruction, and executes it. So let's see exactly how Scott's CPU fetch the instruction. First, in step 1, we want to give an enable pulse to the instruction address register, where there is the address of the first instruction. So we put this address on the bus with an enable pulse. Then we want to acquire this byte that is on the bus. We want to acquire it in the memory address register, because this is the address of the first instruction. So we give a set pulse, always in step 1, we give a set pulse to the memory address register. Then, because the address of the first instruction is on the bus, we want to update it. So we give a bus 1 pulse, and we give, in the same step 1, an accumulator pulse to acquire the result of the ALU operation in the accumulator. Let's see how it works exactly. So we have to think that the instruction, the content of the instruction address register is on the bus, and we want to update this. So we give a bus 1 pulse, so in the input B of the ALU there is the number 1, and in the input A of the ALU there is the content of the instruction address register. Because the opcode is 000, we don't give any signal or any pulse to the opcode, so we don't change the opcode which stays at 000. So with this opcode we perform an addition. So at the output of the ALU there will be the address updated by 1, so incremented by 1, because in the input B there is the number 1. So this result is in steps 1 acquired in the accumulator. So the accumulator contains, after step 1, the instruction address updated. We leave it for the moment, and we go to step 2. In step 2, we give an enable pulse to the RAM to put on the bus the content of the cell determined by the address we have saved in the memory address register. So we put the first instruction on the bus, giving an enable pulse to the RAM, and we acquire it in the instruction register, giving a set pulse to the instruction register. So in this moment we have in the step 2 we give an enable pulse to the RAM, which puts on the bus the first instruction, and we give a set pulse to the instruction register, which saved the instruction in the instruction register, where we are going to see this instruction here in this output I created here, but actually this bit goes inside the control section to decode and then to execute correctly the instruction. Now we stop the simulation when after we have fetched the instruction in the instruction register. So in step 2 we fetch the instruction in the instruction register, and in step 3 we finish what we have started in step 1. So we have updated the instruction address register, we have updated the instruction address, but the content is in the accumulator. We want to save this updated address in the instruction address register. So in step 3 we give enable pulse to the accumulator, so the accumulator put the result on the bus, put the byte on the bus, and we give a set pulse in the instruction address register, so we save the address of the next instruction in the instruction address register. So here we give a enable pulse to the accumulator, which puts in the bus its content, and we give a set pulse to the instruction address register. So after 3 steps, we have fetched the instruction into the instruction register and updated the instruction address register. So now let's run the simulation. First, I put 2 instructions in the RAM. So I use this enabler to put a byte on the bus. So in the address 0, I put the address 0 on the bus. I acquire this address in the instruction address register, and I acquire this address in the memory address register. And we free the bus. So now the memory address register points to the cell 0, and we put inside an instruction. So we give this instruction here. It is an ALU instruction, in particular an addition, but we don't care about what kind of instruction is. We put just this instruction in the first cell of the memory of our RAM. So we put this on the bus, and we give a set pulse here to the RAM to acquire it in the cell 0. Now we put another instruction in the cell 1. So the address 1, we put the address on the bus, we acquire the address in the memory address register, we free the bus. Now we put this other instruction, for example, this instruction here, which is very different, so I can put more ones to recognize it. So we put our instruction on the bus, and we write this instruction in cell 1 of the RAM. So let's see if in cell 1 there is our instruction. We give an enable pulse to the RAM, and this is our instruction. We can see if what there is in the cell 0. So we give a set pulse here to. So let's see what there is inside the cell 0, and there is this instruction. So now what we expect? We expect that after a cycle, so after these 3 steps, we fetch the first instruction in the instruction register. And the first instruction is this one here. So a 1 as first bit, and here another one here. So we expect to have this instruction in the instruction register, and we expect that the instruction address register, which is 0 now, will be at the end of the 3rd steps will be 1. So let's run this simulation. In order to run the simulation, I use this counter, which always has to run just 1 cycle of stepper and then stop. Otherwise, I keep adding, I keep doing the same operation over and over. I don't get the result we expect. So I put here the number 1. So this means that I want just 1 stepper cycle. So let's do it. Okay, you see one step, one stepper cycle is just gone, and now we see here that this is the most significant bit, and this is the least significant bit, because this is 7, this is 0, and you see this is the instruction we have put in the cell 0. Now we want to check if inside the instruction address register there is the number 1. So we give an enable pulse, and we see here there is the number 1. If you remember, we we have put here the number 0. So the instruction address register is updated. But we want to run the other instruction too. So we can give another pulse here, and we perform another stepper cycle. Okay, so let's see here. As you see, the instruction here is the instruction we have put in the cell 1 of the RAM, and we give an enable pulse to the instruction address register to check if there is the number 2 inside the instruction address register. And as you see here, you can see you can read the bus by this output here, and there is the number 2. So the instruction address register is being updated. So here we see the timing diagram. We give a pulse here, and we stop the simulation after a cycle. You see here the 6 steps. In the first step, we give an enable pulse to the instruction address register to put the address of the instruction in the bus. We give a set pulse to the memory address register here, always in the step 1, to acquire the address of the instruction. And because the address of the instruction is already in the bus, we give a bus 1 pulse, and in this way the ALU increment the address by 1, and we acquire this result in the accumulator, giving a set pulse to the accumulator. Then in step 2, we give an enable pulse to the RAM to put on the bus the instruction contained in the cell of which the address we have just saved in the memory address register. So in our example was the cell 0, and so we put the instruction on the bus. Then we acquire the instruction inside the instruction register, giving a set pulse. In step 3, we give an enable pulse to the accumulator, putting on the bus the result of our incrementation, and we acquire the updated address in the instruction address register. So in 3 steps, we fetch the instruction inside the instruction register, and we updated the instruction address register with the address of the next instruction.
Please leave me a comment, let me know if you liked this video, make sure you put a thumb up, click the notification bell and subscribe to my channel.